This is a short summary for Chapter 8, Part 1, focused on the practical use of applicative functors. I motivate applicative functors as a kind of subset of monads where we want to express independent computations or independent effects that occur in parallel, such as accumulating all errors from a number of computations. And in order to do this, we need a method that is not going to stop after the first error, like a monad would. And so that kind of method is called map2. I show the type signature of map2. And most of what we work with in this chapter is based on map2 and its generalizations. I show map1, map2, map3, how these are easily generalized one after another into map n. And I show practical examples of various functors that have this definition, emphasizing that they're different in some cases from monads. So, for example, this one would collect all errors, but it's a different implementation than it would follow from a monad. I also talk about applicative contrafunctors and applicative profunctors. We have talked about contrafunctors in previous chapters, but not about profunctors. So I define what that is, and I show an interesting use case when we can define an instance of semigroup for some case class, given that its parts have a semigroup instance, and that turns out to require a profunctor that has an applicative property, or map2, or it's called imap2 sometimes. I give other examples where fold computations are automatically merged into one so that you have a single traversal rather than separate traversals. And I show code that emphasizes a difference between using applicative and monadic combination or composition of computations, where I show, for instance, what happens if I do applicative merging of different folds as opposed to monadic merging, which I can also define, and this is all shown in the code, how to use that. Another example is parsers. It's a very simple example to illustrate again the difference between applicative combination of parsers and monadic combination of parsers. And that illustrates how applicative computations are independent in some ways, although they can be dependent in other ways on each other, but the structure of the computation is independent on previous results. So what computation is happening next in an applicative combination, the next computations do not depend on the results of the previous computations. The decision to perform those computations is already made up front, regardless of what results there might be. Whereas in a monadic combination, the decision to make the next computation will be made after the result of a previous one is obtained. So I show that using folds and also using parsers in order to illustrate this difference between applicative and monadic combination. And I give some exercises that are similar to the examples I have considered.